Especially when starting with MBSE, it is often quite challenging to really grasp it because sometimes it seems to be that MBSE is a set of kind of untouchable virtual concepts and constructs. That's why we introduced the elements of MBSE in this video. With these elements, we're aiming to ground the term MBSE and make it easier to understand for everybody. To do so, we define three elements of MBSE. The first one is based on Incosi's MBSE definition, stating that MBSE is the model-based application of systems engineering. So, a kind of more theoretical start. The second element focuses on the creation and use of system architecture models as an instrument to work collaboratively in development projects. And the third element pushes the system architecture models beyond its boundaries and focuses on the model-based development approach as a whole. Let's start with the first more theoretical element. Incosi defines model-based systems engineering as the formalized application of modeling to support system requirements, design, analysis, verification and validation activities, beginning in the conceptual design phase and continuing throughout development and later lifecycle phases. So the focus is to use formalized models instead of the SE-driven document-based development approach. To bring Incosi's definition to practical application, two SE perspectives have to be considered and discussed. The first one looks at the principles of systems engineering, and the other is what SE does with these principles. So, for example, create an interface specification document or create a requirements document. But let's start at the beginning. Developing a new system is all about to bring challenges and problems to a solution. It's as simple as that. For that, the framework of processes, methods, organization, and tools is used in general. There is the development process structured into several phases, methods such as CAD or EE circuit design, and engineers who apply these methods with or without specified tools. Mechatronic system development, for example, requires the involvement of several disciplines who are typically not trained to work together. The result may be a huge mess and a weak developed system. Systems engineering provides fundamental principles and best practices such as system thinking, interdisciplinarity, collaboration as a team, early verification, and many more. These principles must be integrated into the development process and should not be seen as something kind of separated from the whole process. In order to focus on the system as a whole, the systems engineer is positioned in parallel to the other engineers to ensure that the system meets all the customer needs. The other thing is what SE does with all the principles and best practices. Of course, from a SE benefits point of view, it makes the development process better by ensuring that all stakeholder needs are met in the most efficient and effective way. And just to be clear, SE is not a cookbook, resulting in a good product when applied automatically. Despite the definition of SE that states developing systems successful, SE provides principles and best practices that must be integrated in your development process. The success of a product development does not come from SE. That's very important. It comes from you and your development team, but it can be supported by SE. Anyway, what SE produces when applied are documents. Documents that document the stakeholder needs, system requirements, systems functionality, system structure, interfaces, tests, and you can think of many more, of course. The application of SE principles typically results in more documents, ensuring to address all perspectives in systems development and ultimately increase the system maturity. And this especially opens the potential for MBSE to create all the documents, or at least some of them, model-based. Let's see how this looks like in our second element of MBSE. The second element focuses on creating system architecture models besides or in addition to all the other models and documents that are typically created in the development process. Many different engineers, like mechanical engineers, electrical engineers, software engineers, are involved in the system development, meaning that different parts of the system with different views are developed. Ensuring that targets, especially the overall system functionality, are met is therefore sometimes very challenging. To keep an overview on the overall system, one approach is to install systems engineers. As we've seen in previous slide, this brings in at least one new person and some new documents that are created. One task of the systems engineer is to focus on the overall system and ensure that all the other engineers work together in an efficient manner. This leads to the importance of system architecture models. These models provide the systems engineer an instrument to align the development team. System models, compared to other models in the development process, are used as common base for the development team, for system documentation, and much more. The cube, which you can see here, visualizes the role the system model and other models have perfectly. The cube is created by 3 axes. Just look at them shortly with me. First of all, the discipline, which shows the different disciplines involved in the development process. We have the technical domains, which describe the different views on the system, and we have the levels, so the structural hierarchy of the system under development. Inside the cube, all the models, also the documents that are used in the development process, are displayed. 2 different types of models are present. System models, which you can see in blue, and specific models, which are displayed in orange. Specific models describe a detailed view on the system. For example, the CAD model describes the system from a structural point of view, from vehicle to engine level, from a mechanical point of view, of course. In parallel, system models are typically available on higher levels, so for example on the complete system or subsystems, and describe the system from several points of view united. For example, the vehicle system model involves the views of several disciplines and domains, but of course then lacks in level of detail. These system models give the systems engineer some new possibilities. Do you guess what they are? Let's consider them together. For example, the vehicle system architecture model can be created with Arcadia Capella or with SystemL by the systems engineer. The system model can be then used as a collaboration hub to align the vehicle functionality with stakeholders, but also with the development team. To consider the system as a whole by defining functions that are developed by different engineers in the development team. Here, besides the definition of the function, the systems engineer must ensure that the function is met. As knowledge store, system models are used as documentation of the system in terms of general structure, interfaces, functions, and main parameters. And development support. An architecture gives the ultimate instrument to ensure that all development team members are aligned and develop, let's call it, the same system. Sounds simple, but is a huge challenge since engineers understand the system in very different ways sometimes. The architecture can definitely help here. And finally, the third element of MBSE, which focuses on model-based development as a whole. Not only the system architecture models, but all the others as well. Typically, various documents are created by different engineers in different phases of the development process. This could be a system requirements specification document, a use case specification document, or a system test specification, besides many more. In parallel, also various models are used, such as a ECAD model, a MCAD model, or a FEA model. When required, they are sometimes also connected. Documents in general are not a bad thing, I want to state that here, but when it comes to complex systems, the involvement of several disciplines and larger projects, documents are kind of a limiting element. This means there is a shift from considering a more document-based development to a more model-based development approach. Information described in documents is now described in models, but when documents are required, they are derived from the models. Models allow to store and manage large amount of information of the system or form various views of the system. If required, models are connected with other models to exchange certain information. To manage models and the information that is exchanged, PLM systems can be used, but this strongly depends on organization-specific dependencies. Anyway, the shift from document-based to model-based development requires to rethink existing development processes, methods, tools, and even organizational roles. Only when aligned to the new form, model-based development benefits such as traceability, centralized information, enhanced collaboration, and many more are given.